Okay, in this video we are going to look at Kb. So we've looked at Kc, Kw, Ka, now we're going to look at Kb. So Kb is for bases. So remember we talked earlier about how when we're in the equilibrium unit, we're mainly going to be dealing with weak bases. And that's because we want to actually reach equilibrium, and we're only going to reach equilibrium with weak bases. Okay, most weak bases we're going to find are going to have a little negative charge. So we tend to use the symbol of a B- to kind of represent a generic base. Okay, the reason we do that, if you have a look in your acid-base table, if we're looking here in the base column, you'll see how they pretty much all have negative charges, right? It's a couple exceptions. I want to say we get down to the next page here. Sorry, I gotta flip it around. You'll see there's like ammonia, which doesn't have the negative charge, but I want to say for the most part, that's kind of your only exception with respect to bases that you're going to have to deal with on a regular basis. But yeah, most of the time they're going to have that negative charge, and you're going to be able to recognize that they're going to be a base based off of that. So if you look at our equation, same type of deal as what we saw with the acids. We're going to react with water. Obviously, in this case, we're going to form hydroxide because the transfer is going to be this proton moving from water over to the B- to give us an HB. When we write our Kb expression, our generic one, it's going to be the concentration. I don't know why that says HB plus. It should just say HB times OH minus, and that would be over the B-. Okay, so remember, no water because water is a liquid and we're not going to include it. Obviously, when you are answering questions, please make sure that you write your Kb expression that is specific to the equation that you've written. I did notice in marking your unit tests that some of you did write them, and some of you, even though we talked about not writing like products over reactants, that was still what you wrote for your Kc. So really important to make sure that your K, or your equilibrium law expressions, are specific to the equation that you've written. Okay, so if you look in your data booklet, right, so if I flip back to that, where do I have that? Oh goodness, computer did something weird when I restarted it. Oh, no, it's not there. Where'd it go? No, that's not right. Maybe I closed it. Hold on. So when we are looking at our data table, right, we are only given Ka. So that means for bases, we're going to have to do a little bit of work to figure out what the Kb is. So there's a relationship, though, between the Ka and the Kb for conjugate pairs. So if we go back and revisit what are conjugate pairs. So when we have conjugate acid-base pairs, hold on, give me 2 seconds to figure out what I'm trying to say. So when we have pairs, sorry, my brain is not functioning properly, and the fact that these arrows are missing is really bothering me. Okay, let me fix that. Okay, what was I trying to say? So we talked about conjugate pairs, right? We talked about how you have a species on this side that pairs up with something that's over on this side, right? So CH3COOH and CH3COO-, right? These two are conjugate pairs to each other, right? And they're conjugate pairs because this has the hydrogen and this one doesn't, right? And we said earlier that conjugate pairs differ by one having the proton and one not having it, okay? So in this particular case, because we started with acetic acid and we produced hydronium, we would be writing a Ka for this, right? We used an acid, right? And if I look at the two conjugate pairs, I know that this is the acid form because it has the extra H, and I know this is the base form because it's missing the H, okay? So if I were to write the Ka for this, I would have the hydronium times that acetate ion divided by the acetic acid, no water going into the equation. So if we looked at the equation for the conjugate of acetic acid, right? So if instead of starting with this, we started with this, okay? The equation doesn't flip around because we are actually still going to be combining it with water. So if we look at this equation, we have the CH3COO- combining with water. It's going to give us CH3COOH and OH-. Okay, so still combining with water, we still have our conjugate pairs happening here. We are now obviously making hydroxide because the acetate ion is a base and it's not an acid. So if we wrote the Kb for this equation, we'd have the CH3COOH times the OH- divided by that CH3COO-. So this may seem kind of random, but if we multiply the Ka and the Kb of these conjugates, right? So if we actually do that, thought I had this typed out, apparently I didn't. So if we do the Ka times the Kb, fix my font because it's massive. Okay, actually using the expressions that we wrote, right? So for Ka, we had this H3O plus, so we're going to say concentration of hydronium times the concentration of that CH3COO minus, right? And that was over the concentration of CH3COOH, which obviously went back to the ginormous font size. Okay, let's fix that. There we go. All right, so there's my Ka. I want to times it by my Kb. So I'm going to do times what do we have? CH3COOH times OH minus. That's not an H. Hold on, there we go. And that is going to be divided by that CH3 COO minus. Okay, so now if you look at this, we just did the Ka times the Kb. You should notice that we can get rid of some stuff, right? This CH3COH is going to cancel this CH3COH. So we get rid of that with that. The other thing we can get rid of is the CH3COO minus, because there's also a CH3COO minus over here. So what we're left with is hydronium times hydroxide. Okay, we have another equation that's also hydronium times hydroxide. Right, so right now we're saying that Ka times Kb is equal to that hydronium times the hydroxide. Okay, if you figured out by now what that other equation is, hydronium times hydroxide, it's Kw. So what that means is Ka times Kb equals Kw. Okay, this is only true for conjugates, okay? So only for conjugate pairs. This isn't true for random things that have no relationship to each other, okay? So what that means is even though my data book, some pretty awesome squiggly lines here, maybe highlight it, do something that looks prettier than that. But yeah, so what that means is even though my data booklet only gives me Ka, I can still figure out what Kb is. And that's because Kb is going to equal Kw divided by Ka. So if I was trying to, let's say, figure out what the Kb was for ammonia, I would look up its conjugate, or I could also just find it in the base column, right? So I could go to that data book, see if I can figure out where I hit it. Oh, there we go, right? So whatever we're looking at, let's say we're using ammonia, because that's what I keep talking about, right? So here's ammonia. I don't think that markup's going to work. And here's the ammonium. So I find ammonia in the base column. There's the Ka for its conjugate. So to figure out what the Kb is for ammonia, I'm just going to do Kw, which remember is 1 times 10 to the negative 14, and it's in that miscellaneous table, divided by the 5.6 times 10 to the negative 10. And then that is going to give me the Kb for ammonia. So what that does mean is most of your base questions are going to need at least one additional step. Okay, and that additional step is going to be to figure out what the Kb is. Okay, obviously if it's giving you other information like to fill the whole ICE table and it's asking you to figure out Kb, then you're going to do that. But if it's basically asking you to figure out X, you have to know Kb. So you're going to have to come to this data table, find the Ka for the conjugate, and then convert it over to a Kb. Okay, when you do that though, you do have to be careful because you're going to get a messy number. It's going to have a lot of decimal places, and you need to make sure that you carry those numbers through into your calculation. Okay, so now that you know how to find Kb, let's look at some questions. So really simple one, right? What is the Kb for the carbonate ion? So what we're going to do is we're going to go to our red book, which I've hidden back here. We're going to find the carbonate ion. Okay, so here is the carbonate ion in the base column. It's at the bottom of that page. Okay, the Ka is 4.7 times 10 to the negative 11. So to get the Kb, we're going to do the Kw divided by Ka. Okay, so we're going to do, oh, hold on, I'm not hitting the right buttons, 1.0 times 10 to the negative 14, right, because that's Kw. And then we're going to divide by Ka, which was 4.7 times 10 to the negative 11. Okay, once we do that, that's going to give us what our Kb is for this. Calculator's in a weird setting. Okay, 1 times 10 to the negative 14 divided by 4.7 times 10 to the negative 11. So we're going to get 2.12, and that number keeps going, times 10 to the negative 4. Okay, so from here, if all the question was asking me for was the Kb, obviously I would round that to 2 significant digits. So I would say it was 2.1 times 10 to the negative 4. If the question was asking me to go further than that, then I would go ahead and I would use that unrounded number. In this case, it's only asking me for what's the Kb, so we're going to go to 2 significant digits because the other numbers we used all had 2 significant digits. Okay, so let's have a look at this one. So now we're going to actually look at calculating something besides just figuring out a Kb using our data table. So it says calculate the pH of a 0.01 mole per liter solution of sodium cyanide. Okay, I feel we need to change this to 0.1 because I feel otherwise we can't approximate. And I want to approximate right now. So change the example to 0.1. Okay, so we've talked about approximation before. Again, we also talked about how the majority of the times in this unit you're going to be able to approximate. Definitely going to have some questions where you can't. But I'd probably say more often than not, you are going to be able to approximate, right? So remember, you're going to take that initial and you're going to divide it by your K. If it's greater than 1,000, you're going to be able to approximate and get rid of that X on the reactant side. Okay, so there's also a second additional thing that we have to do with bases. One of them was to figure out the Kb. The other one is to dissociate our compound, okay? In the first slide of this, we talked about how bases generally have a negative charge. Well, I can't just have a negatively charged ion. It always has to be with something else. So generally, how we introduce these kinds of bases into solution is by putting an ionic compound into water. Because it's ionic, it's going to dissociate and break apart. Then we're going to be able to actually do the reaction with water. So we have sodium cyanide, which is NaCN. Okay, we are going to put it into water. Or why am I doing that? Don't know why I'm doing that. My brain is not functioning very well. Okay, so we have sodium cyanide. It is an ionic compound. Because it's an ionic compound, it is going to dissociate, right? When this dissociates, it's going to give us a sodium ion. Along with a cyanide ion. Okay, so at this stage, I need to decide which of these ions is the one that I actually care about, right? One of them is either an acid or a base, and the other one is probably going to be neutral. So hopefully by now you recognize that sodium is pretty much always a spectator. The other way I could recognize that if I go to my data booklet and I look at that acid-base table, the sodium ion isn't in either column, so it's a nothing. But what I do find is the cyanide, right? The cyanide, or the Cn minus, is found in the base column, right? So if we look at that, I want to say it's somewhere down here. Yeah, right down here. There's that Cn minus. So that's how I'm going to decide which of the two ions I actually care about. So dissociate it. Once you have dissociated, figure out which ion is the one that's either the acid or the base. Most of the time it's going to be base. And then I can actually react it with water and start setting up my equilibrium. Okay, so we have that. it's going to be in equilibrium with HCN. And an OH minus. Right, we have to transfer the proton because this has no proton, it can't donate to here, so we have to be taking a proton from here and moving it to here. Okay, so we set up our base table. Okay, we're going to X out the water, right, because the water is a liquid. We're not concerned about it. Okay, so we are given the concentration of sodium cyanide. We look at this equation, you should be able to recognize it was a 1-to-1 ratio, and therefore the concentration of the cyanide is going to be the same as the sodium cyanide. If it wasn't a 1-to-1 ratio, then I would want to make sure that I account for that down here, right? If this was balanced with a 2, I'd want to make sure that I do my little stoic calculation to figure it out. But at this point, if it's a 1-to-1, I'd like to think you guys are capable of recognizing that, and I don't really need to see the work for that because I'm not going to be awarding you marks for that. If it was like a 2-to-1, then potentially there would be some marks for it, but there might still not be because really that's a Chem 20 thing. You should be able to do some pretty simple ratios. Okay, so HCN and OH minus, they're always going to start as 0. Okay, you're going to find the acid-base equilibrium. We never worry about if we're given the concentration of everything because that's never going to happen. We're always only going to have the reactant. Okay, so minus X, plus X, and plus X. Okay, so our equilibrium values are going to be 0.1 minus X, X, and then obviously another X. Okay, so we've now set that up. We need to get the Kb for the cyanide ion. Okay, the way we're going to get the Kb, we are going to do the Kw divided by the Ka. Okay, so we're going to have our 1.0 times 10 to the negative 14. And then, well, cyanide is 6.2 times 10 to the negative 10. Okay, and then from here we can figure out what our Kb is going to be. Should I type that in right? Okay, so our Kb is going to equal 1.61. That's going to keep going, times 10 to the negative 5. Now that we have a K, next thing we want to do is we want to do a quick approx check, right? So to do our approx check, we're going to take this 0.1 and we're going to divide it by the K that we're going to be using. We get 6,200. So that is a yes to approximation, right? We can approximate, that's greater than 1,000. So that means on our reactants, we are going to get rid of that negative X, right? It only impacts the reactants, no impact on the products. Okay, next thing to do is set up our equilibrium law expression. So we have that Kb is going to equal the concentration of HCN times the concentration of OH minus, and that's going to be divided by that concentration of Cn minus. Okay, so we have the Kb, which was that 1.61 times 10 to the negative 5. Please make sure you're using the whole number, not just the rounded number. Okay, and that's going to equal x squared over 0.1. Hold on, I got to extend my page. There we go. X squared over 0.1. Right, so we are able to get rid of the minus x, which does make this a much nicer question to actually solve. So from here, what are we going to do? We're going to take our K value. So I'm just retyping it in so that I have that whole number. Then I'm going to times it by 0.1, and then I am going to take the square root. Okay, and I'm going to come up with the fact that x is equal to 0.00127, and that keeps going. Okay, again, if you prefer to graph it and solve for x, you can. Same deal if you didn't realize you could approximate and you graphed with that additional x in, really not a big deal. It's not going to significantly change anything, okay? So now that I've solved for x, what is the question asking me for? The pH. So we know that x is equal to the concentration of hydroxide. So kind of two options. You can either solve for the POH, because you know the concentration of hydroxide, and then convert the POH to pH by doing 14 minus. Or you can use the concentration of hydronium times hydroxide equals Kw. It's kind of up to you. I find the majority of the time, you guys at this stage prefer to calculate the POH by saying that it's the negative log of the hydroxide, which in this case is our x value, right? So we're going to have negative log of our answer. We're coming up with 2.896. Okay, then to get our pH, we are going to do 14 minus that POH, which is that 2.896. Again, make sure you're using the whole number, not the rounded number. Okay, significant digits. I think the concentration had one number after the decimal. Yeah, it was just 0.1. So that means we are allowed to have one number after the decimal, right? That 0.1 only had one significant digit, so we get one significant digit in our pH. Remembering pH is only the number after the decimal that counts. So we come up with 11.1. Always make sure with these kinds of questions you stop to make sure that your number makes sense, right? I have a base, it's a weak base. pH of 11 sounds about right when I'm dealing with a weak base, okay? So yeah, that's kind of how you're going to do questions like this. You need to write your dissociation equation, set up your ice chart with whichever of the ions is the base. You're going to have to calculate Kb using Kw equals Ka times Kb. Do your approx check, then set up your Kb expression, plug your numbers into it, solve for x. Once you have x, you can go ahead and solve for the POH and then figure out what your pH is going to be. Okay, we talked about amphiprotic species before. We said that these are species that have the ability to either be an acid or a base, right? So we talked about how water was amphiprotic, and we also talked about how things with H and a negative were amphiprotic. So when we're combining something with water, it's usually pretty easy to figure out if water is going to be the acid or the base just based off of what is the other thing. But if I combine something with water where that something is also amphiprotic, then I have to figure out whether that other species is going to be an acid or a base. Okay, so what I'm going to have to do is basically compare the Ka and the Kb, right? So if I was looking at, I don't know, what's a good example? Like, let's say HPO4 2-, right? It could be an acid because it still has an H, but it could be a base because it has two negatives. So I would have to figure out what's the Ka for it, and then I would have to calculate what's the Kb for it. And then basically I'm going to compare them. And if I find that the Ka is greater than the Kb, that means its acidic properties are stronger and it's going to behave as an acid. If I find, on the other hand, that the Kb is bigger than the Ka, then that means its basic properties are stronger and it's going to behave as a base. So let's look at an example of a question like that. So it says, what is the pH of a 0.265 molar sodium hydrogen carbonate solution? So I have sodium hydrogen carbonate. I should be able to recognize that that is an ionic compound. So because it's ionic, we're going to dissociate it. Okay, this is going to break apart into a sodium ion. And a hydrogen carbonate ion. Okay, so next step is I need to figure out which part I care about. So if I go to my data book, right, hopefully by now I recognize that sodium I never care about. But if you look in your book, right, now we're looking for hydrogen carbonate somewhere in here. Okay, so here's hydrogen carbonate in the base column. But if I keep scrolling in my table, here's that hydrogen carbonate as an acid. So it could be an acid or it could be a base. It's an amphiprotic species. So I'm going to have to compare the Ka to the Kb that I calculate for this one here. Okay, so Ka is pretty obvious, right? For hydrogen carbonate, I have to find it in the acid column if I'm looking for a Ka. Okay, so whenever I'm looking for a Ka, I'm looking for something to be in the acid column. When I'm looking for something to be a Kb or a base, I am looking for it in the base column. So here's the hydrogen carbonate in the acid column. So the Ka is 4.7 times 10 to the negative 11. Okay, so when we're dealing with this guy here, we have a Ka equal to 4.7 times 10 to the negative 11. Okay, now I have to figure out what's going to be the Kb for this, right? The way I'm going to figure out the Kb is by doing the Kw divided by the Ka. Okay, so this is where you have to be careful, because if I'm looking for the Kb, I need to find it in the base column. And a lot of times what you guys want to do is you want to use this Ka of 4.7 times 10 to the negative 11 to figure out the Kb for the hydrogen carbonate ion. But if you look at this 4.7 times 10 to the negative 11 is associated with the carbonate ion as the base. So this is not the Ka I want to use, right? I want to find the hydrogen carbonate in the base column, which is up here. Okay, its conjugate acid is carbonic acid. So I want to use the Ka that's next to it, of 4.5 times 10 to the negative 7. So for amphiprotic species, when we're comparing the Ka and the Kb, we are not using the same Ka number when we do that calculation, because there's different Kas, because we're looking at hydrogen carbonate in two different spots on the table. So to calculate the Kb, we're going to use the 4.5 times 10 to the negative 7. So we're going to do 1.0 times 10 to the negative 14. We're going to divide by 4.5 times 10 to the negative 7. Right, so not the same Kas, because this Ka is for this as an acid. This Ka is for when the hydrogen carbonate was in the base column. So let's figure out what it's going to be. So 1 times 10 to the negative 14 divided by 4.5 times 10 to the negative 7. This is going to equal 2.2, and that 2 just keeps on going, times 10 to the negative 8. So now I need to decide whether it's going to be an acid or a base. So I'm going to compare the Ka to the Kb. So I have times 10 to the negative 11, and I have times 10 to the negative 8. We said whichever one was larger was what it was going to behave as. So in this case, it's going to behave as a base, because times 10 to the negative 8 is larger than times 10 to the negative 11. So now I know what's the appropriate equation to write for setting up my ice table, because before I do this, I might write an acid equation, I might write a base equation, but because the Kb was bigger, I know it's going to be the base. So we're going to have HCO3 minus, we're going to combine it with water. Okay, this is going to set up an equilibrium. I'm setting up an equilibrium because it's weak. Okay, because we've decided it's going to be a base, right? Think back to what we said the definition of a base was for Bronsted-Lowry. A Bronsted-Lowry base is going to accept a proton. So that means this is going to turn into H2CO3. And that's going to be plus hydroxide. Okay, most common mistake you guys make in a question like this is as soon as you see the H, you guys want to jump to the conclusion that something is an acid. In this case, that would result in very limited marks on the question, because this is definitely not an acid, it's a base. And if I set up the wrong equation, everything, my ice table is going to be wrong, I'm going to have the wrong K expression, obviously I'm going to have the wrong X, and my final answer is going to be incorrect as well. All right, let's make an ice table. Capital I, C, E. doing next? I am going to cancel out the water from this ice table because the liquid. All right, so pH of a 0.265 molar sodium hydrogen carbonate solution. So when I look at my dissociation equation, everything was a 1-to-1 ratio. So that means the initial concentration is going to 0.265. This is going to start at 0. This is also going to start at 0, right? Minus x plus x and plus x. Okay, so equilibrium values are going to be 0.265 minus x, and then x and x. All right, approx check. So 0.265 divided by our 2.2 times 10 to the negative 8. We get a ginormous number. So with respect to approximation, we definitely can. So that is a check. We're going to get rid of this. Right, just on the reactant side. Okay, so Kb expression. We're going to have that Kb is equal to concentration of H2CO3. Oh, I forgot to underline that. I'll fix that in a second. Times hydroxide. And that is going to be over the concentration of HCO3 minus. Okay, so we have that Kb, which was 2.2 times 10 to the negative 8. And that is going to equal our x squared divided by 0.265. Right, because again, we were able to approximate. Okay, so figure out what we get for x. That was not the right button. I hit sign. Okay, so we have our 2.22222 times 10 to the negative 8. We're then going to times by 0.265 and get the square root of our answer. And we're going to come up with x is equal to 7.67 times 10 to the negative 5. Question asked, I'm assuming for pH? Yeah, pH. So we know that x is equal to the concentration of hydroxide. So we can figure out the POH because it's going to equal the negative log of the hydroxide, or in this case, the negative log of x. So we can do negative log of our answer and come up with 4.114. That number keeps going. And then to get the pH, we are going to do the 14 minus our POH, so minus 4.114. And we're going to come up with the fact that the pH is equal to significant digits. What do we have? 3. So 3 numbers after the decimal. So 9.885 is going to be our pH. Okay, so your KW, your KA, your KB, those don't count for significant digits. They're considered constants, and we don't count constants when we're looking at significant digits. So the only given I had in the question was the initial concentration of 0.265, which had the 3 significant digits, which is why we're going to have these 3 numbers after the decimal place. Okay. This one just adds a little bit extra in that you have to actually calculate the initial concentration of the solution, okay? I don't want to say KB is kind of as hard as it gets, but this is kind of as hard and as complicated as it gets when we're looking at our K calculations, just because there are so many additional steps that you have to do. And this is where it's really important to make sure that you feel confident with your K calculations. Usually between the 2 units of equilibrium and acid-base equilibrium, this is the one you guys struggle with more because it's more complex. There's more things happening, right? We take something that started out as like, okay, this is kind of complicated, and okay, now I feel comfortable with this. And then we just kind of keep tacking stuff on. And adding things to it, right? And there's still, I think, 3 more lessons left in this unit. So yeah, it definitely does start to get more complicated, and this is where that practice piece is super crucial, where again, you're going to find like you're going to have some people in the class that it's like they just get this, they're very mathematically inclined, and like they do a couple of practice problems and they're like, I got this. And then there are some of you where you're going to find like I've done 10 practice problems and I still feel as though I have no clue what I'm doing. And really the only way to fix that is just keep practicing and keep practicing. And then what you find tends to happen is when you go write that quiz, you go write that unit test, you start to just be like, okay, I've seen something kind of like this before. Whereas if you don't practice at all, you're going to find you go to write those and you're just going to be like, I don't know what to do. I don't know what to start. I don't even know what my first step is, right? And so that's where really important to make sure that you are practicing until you're feeling like, you know what, I feel okay with this. Like there's a couple questions that definitely stump me, but for the most part, I'm feeling pretty confident about this. So yeah, so looking at this last one, I think what I'll probably do is I'm just going to pause it. Maybe you guys can pause it, give this a try in class, maybe in like 5-6 minutes, throw it back up. And I will give you the solution to this, okay? All right, so we're taking ammonium chloride, which is NH4Cl. Now, I should start this as a solid because I was given a mass for it. So we are going to be placing this into water. So we have our arrow, our H2O. That's not a subscript. Go. Okay, and this is going to give us the ammonium ion and the chloride ion. Okay, the part I care about is going to be the ammonium ion. Okay, it's not the chloride ion. If I look at my data booklet, although the chloride ion is in the conjugate base column, it's in that very first 6, right up here. Remember we talked about how these 6, although they're in that base column, are not actually going to be bases. So that's not going to be the part that I'm caring about. The part that I'm caring about is going to be that ammonium ion. So first thing I'm going to have to do is actually calculate what is the concentration of that ammonium ion, because I'm going to need that to be able to set up my ICE table. Right, so we were given a mass of this as 2.5 grams. We were given a volume as 0.1 liters. Because we have a mass, we need to go get a molar mass. Okay, it's going to be, double check that I did that right, 53.50 grams per mole. Okay, so calculating the concentration of the ammonium ion. We're going to do our unit analysis, so you should have the 1 mole of the ammonium over 1 mole of the ammonium chloride. Okay, to get rid of moles of ammonium chloride, we are going to times by the molar mass, so moles of NH4Cl divided by 53.50 grams. Right, so we had to flip that so that we could cancel out moles of ammonium chloride. Okay, now to get rid of the grams, we're going to times by the 2.50 grams. And then last thing we need to do is get those liters in, and they need to go on the bottom. So we're going to times by 1 over 0.100 liters. Okay, from here, we can figure out that our concentration is going to be 0.4672897.196 moles per liter. Okay, from here, set up our equilibrium expression. So we have the ammonium ion plus water. It's going to be an equilibrium with ammonia. And hydronium. Okay, how I know that I was making ammonium, when I look for it in that acid table, right? It's right here. It's in the acid column. So because it's an acid, that's why I know it has to behave as an acid, and it is going to produce that hydronium. Okay, so there are some acids that follow that same starting point as a base, and this is one of those examples, okay? And that's just because the ammonium has a positive charge, right? I want to say it's the only one that's an acid that has a positive charge that's in your booklet that I'm currently seeing as I glance at it. But yeah, so it looks a little different. So we set up our ice table, right? So you should be starting to recognize that one of the most important steps when you're in this unit is actually going to just be figuring out whether you have an acid or a base. And you're figuring all that out using that acid-base table in your data booklet. So finding things and figuring out what column they're in to make sure that you write the appropriate equation. Okay, water goes away. Initial concentration of the ammonia is going to be 0.467. The other two are going to start at 0. Okay, change values, minus x, and plus x. Okay, our equilibrium, 0.467 minus x, and finally x. Okay, I want to do an approx check. So the Ka for ammonia is 4.7 times 10 to the negative 11. Definitely getting a number that's way bigger than 1,000. So that is a yes to approximation. We can get rid of that. Okay, so next thing we need to do is set up our equilibrium law expression. So that is going to be the Ka equals concentration of the NH3 times the concentration of the H3O plus divided by the concentration of the NH4 plus. Okay, Ka, we're looking it up in our data booklet, 5.6 times 10 to the negative 10. Okay, and that's going to equal our x squared divided by that 0.467 number, okay? So 5.6 times 10 to the negative 10 times that entire number that we got, so our answer. We're going to figure out what that is, and then we're going to take the square root, and we're coming up with sorry, I'm trying to extend the page. There we go. That x is equal to 1.617 times 10 to the negative 5. Okay, so that is representing x, which is giving me the concentration of the hydronium ion. Question asked me for what? The pH. So we know that pH is negative log concentration of hydronium, which in this case is x. So we can do negative log of our answer. Okay, significant digits. What did we have? So the mass and the volume both had 3 significant digits, so we can go to 3. So we're going to have 4.791. This makes sense, right? We have ammonia, it's an acid, it's a weak acid. I would expect a pH kind of between 2 and 6 for that one, okay? So this is what Kb looks like. This is what you have to do for amphiprotic. Recognize that you're going to have to write those dissociation equations when you're given that ionic compound. Figure out which part it is that you are interested in by looking at your acid-base table. Then write the appropriate ionization equation, either producing hydronium if it's an acid or a hydroxide if it's a base. And then from there, you can look at doing your next part of your calculation. Okay, so that is Kb.